Good morning. Thank you all for being here. I'm Charles Poe, Manager of Discrete Computation at Wolfram Research. Today I want to give you the latest update on the geometry in the upcoming version 13 of the Wolfram language. So in this talk, I will cover usability, which is kind of one of the key components we continuously improve in every feature. And I will also kind of give you an overview of the new basic region as we continue to add new representation for geometric region in the language. And on the analytics side, I will talk about the region transformations and end up with the two main key features for this release, which are region reconstruction or surface reconstruction in that specific case, and constructive solid geometry, which is the new modeling scheme we are adding to the language. Okay, in terms of usability in 13, we try to continuously integrate all the new graphic primitive to geometry, as well as taking all the geometric primitive we are adding and make them graphic primitive so you can visualize them as well as compute on them. So in this release, we made sure to actually integrate all the existing geometry transformations into geometry. So for example, if you take a rectangle earlier, if you take a rectangle and you rotate it, it was not a region. So in this coming release, you can check that it's region Q and you can actually compute on it. So the same applies for geometry transform, rotate, translate, and scale, all in dimension 2 or dimension 3. So which is kind of a nice feature in terms of usability. So you don't have any more to discretize it or try to convert it into a mesh or any other representation. So they will just work as geometric regions. Next, we continue to integrate, our main key, option, working precision to all the function in geometry. So as you know, representation, right? For example, implicit representation is general enough that, it kind of, in some case, harder to be able to compute some property like volume. In this example, I have essentially the intersection of two infinite regions there. Actually, in this case, it's just kind of a simple two regions. So these are the intersection of two balls. So you can actually easily compute the volume and we can actually, interesting in my build today. So in principle, you can compute, the intersection, that's a typo here. Wait. So you can actually construct this implicit region, which is the intersection of, two balls, and we can actually compute it and return you the closed form, exact closed form. So behind the scene, we apply, use all our symbolic computation to be able to compute it. So this is kind of just immutable integrals. And there you get the results. And it took some time to actually get that, that answer, as you see. So in the second example here, I just take a little variation of it, and then I just, add a -1 + 1. So essentially, I compute the intersection of two infinite regions. So this computation is actually harder. And, that expression is actually harder to compute. And so what we did in the earlier version, and we continue to do progressively, is to add a working precision option to all the function in geometry. And by default, that working precision is set up to automatic. So we try to decide, during the whole process, if we can actually compute that, that volume, in this case, exactly, or if not, can we actually approximate it? So in this case, we find out that it will be harder to actually compute it. Maybe it will take, I don't know, a day or so to compute it, or maybe we don't yet have all the algorithm or the technique to compute it. So we fall back into, an approximate result, which is mainly through discretization. And as you see here, volume have a working precision goes to automatic. So that's kind of our plan in general, is to take, working precision, add it to geometry, so that you are able to actually to easily work, and it doesn't interrupt your workflow, or the functionality is fast enough to give you the results or the output you want. So in terms of usability, we did a push in terms of integrating more primitive from graphics, and we continue to push, working precision, as well as precision goal and accuracy in the whole framework. So now in terms of basic region, right, we added, essentially two, torus and field torus, which have been requested. So those are kind of quadratic surface. So now torus first exists in the system and is a geometric region. And in this case, torus is the surface, right? If you really think about it, it's essentially like sphere and a ball. So torus is the surface of a field torus, where, sphere is the surface of a ball and the ball is the full dimension object. So it's a geometric object region, and you can actually compute on it as any other region. You can discretize it, compute the area and such. And you can do the same for field torus. So it's a geometric region. You can compute the dimension. Here is the dimension 3, and you can compute the volume, and then you get the volume there. So those two regions are geometric region as well as graphic primitive. So they visualize also in graphics. So if you do graphic 3D of torus or field torus, you actually get this nice picture of the torus. So those are kind of the two basic primitive we are adding, and we hope that in future version we continue to add more basic primitive to the geometric language and extend it, and you get more representation of the object you need to manipulate. Now, in terms of, so those were kind of in terms of, region and new object. So now when we come to the analytic side, in this release, we added, 3 new functions for region relation as well as region transformations. So the first function is region congruent. So essentially, if you give it 2 regions, essentially it tries to find a region congruent, give you true or false if the 2 regions are congruent. So essentially, if there are rigid transformation from one to another. So if it's a if they're coming from a rotation, a translation, or a reflections. So in this case, I take a rectangle and I just ask, is it congruent to a parallelogram? And it's obviously congruent. And we also added the function find transformation, which actually gives you that affine transformations. So in this case, it actually gives you the transformation, which is represented as a transformation function. And you can look at the matrix up there, which kind of gives you that transformation, which is an affine transformations. So region similar, as it says, it tells you if 2 regions are similar. So on top of translation, rotation, reflection, you have also scaling, actually uniform scaling of your region. So if you can uniformly scale your region in both X, Y, and Z, and in 2D XY, you will have regions similar to give you 2. So in this case, I take the parallelogram and just rescale the XY, and you get 2. And if you run find region transform, you actually get the affine transformation. So we have the relation, which are essentially region congruent and region similar, which tell you if 2 regions are congruent or similar, and find region transform, which actually give you the actual transformation. And you can take this transformation, use transform region or any other function to actually manipulate your geometric region like that. Okay, so after the analytic part, in this release, one of the main key components we added is region reconstruction. And I will say this is actually the first step in terms of our set of features we are going to add for region reconstructions. And we hope, in the next future, we'll have more and more functions which will allow you to take data and actually reconstruct a geometric region or approximate a geometric regions. So the first function we introduce is region fit. So this function tries to find the best fit, or it tries to find a region that best fit a data set, and this is actually parametric region, right? So essentially, if you have a set of points, you want to find the plane which best fit those set of points, or you try to find a cylinder which best fit those set of points. As you think, as you see, a plane or a line or a cylinder have an explicit equation. So behind the scene, we run a ransack method, a random sampling techniques to actually be able to compute or find those best fit. So let's take this example. I just have a set of points there, and I try to find the best fit. It returns you here a cylinder with the point and the radius. And you actually can see the point, the object here. So we have a set of points. You have the outlier and you have the inlier there. So in this function, fitted region can actually also give you more properties. So it can give you those outlier, inlier, as well as distance, and you can actually analyze them. It's actually quite efficient function. Behind the scene. It you use all the power on your computer, multi-process, and try to take advantage of everything, and can work actually on large data set. And so that function essentially for this release will in dimension 2 fit line and circle, and in dimension 3 you'll fit line, circle, plane, sphere, cylinder, and cone. And we hope that in the next future release, we'll kind of add all the other region we have, like rectangle, ball, and such progressively to actually be able to support all our parametric region or parametric constructors. So the next object we introduce, or the next function we introduce in terms of region reconstruction, is concave hole. So the key idea in concave hole is essentially if you have a set of points, all right, in 2D or 3D, essentially you want to cover them with balls. Essentially you select the basic cells from a Delaunay triangulation which are contained in a ball of certain radius. So in this case, we generate a set of points in dimension 3. So this kind of gives you a surface there from an equation, and you can call concave hole, and it reconstructs your mesh from that. So as you see here, I'm not actually giving that parameter of alpha, which describe the ball. And usually people call it, the alpha shape in general. So in this case, we kind of automatically determine what's the best parameter alpha to reconstruct your surface, right? And you get actually a nice surface there. So this example essentially show you the case of when you can pick an alpha. So here I kind of, get from our example data, the standard Stanford Bonnie, pick a set of points, 3,000 points here. So if I display them, I get the Stanford Bonnie here. And I can run concave hole mesh on that. And here, in this case, I have a parameter alpha. And you can actually change that parameter quite live and see the change on your construction here. And the key idea of concave hole is that when alpha is big enough, you end up with a convex hole to actually cover the convex hole. And when alpha goes to 0, you actually kind of roughly end up with an empty set. So we have first region fit, which does that fitting, best fitting for parametric region. Concave hole, which take a set of points and essentially try to reconstruct a subgraph of the Delaunay triangulation based on a parameter alpha. So the next reconstruction technique we introduce is gradient fitted mesh, which is essentially what people usually call the Poisson mesh or Poisson surface reconstruction, right? So essentially, if you have a set of oriented points in 2D or 3D, you can actually pretty much solve the Poisson equation on top of it to determine, to find out that indicator function, which gives you the boundary of your set you want to approximate. So this example just take the Beethoven example from our example data, it's a data set which have point as well as normal. So there we have actually that set of points which represent the bust of Beethoven, I think. And you can actually then run gradient fitted mesh on it. And then you get the reconstructed surface. And depending of the, your sampling point and such, it may give you a closed set and in general, you actually try to reconstruct a smooth surface from it. And behind the scene also, this function is, use all multi-threaded and it's quite efficient based on the set of, data set you can give. So you can give me a large data set and you can actually operate on it quite nicely. And we automated a lot of a lot of features. So if you give us a data set without a normals, we can actually reconstruct the normal by approximating them by looking at the, the closest neighbor on the, and reconstruct the plane and construct the normal from it. So there's a lot of automation we added to gradient fitted mesh to actually be able to do, a good fitting for you. And what we hope in the, in the future is to introduce, essentially a general function for mesh reconstructions where you don't actually be, don't need to be a specialist to know which one to use. And we are going to try to do that automatic detection of the right model for you and compute it and return you the appropriate mesh based on maybe some specific goal you can specify it or not. And also, plan to add more approximation function for your mesh. So for example, you can take a mesh and convert it to a smooth surface back and forth and such. So this is kind of the plan we think in long term for mesh reconstruction. So this is kind of the initial step. We gave you, convex hole mesh, region fit, and gradient fitted mesh. Okay, next, one of the main key functionality, beside region reconstruction are constructive solid geometry. So which is roughly speaking another scheme in terms of modeling or solid modeling. Right? As we know, we have surface modeling pretty much with boundary mesh and mesh region, and we have implicit representation. So constructive solid geometry is another scheme for modeling, and in this case, especially for solid. So in this scheme, you represent essentially, geometric region has nested combination of union intersection of some basic primitive, right? And the basic primitive here are, you can think about it as cell, that balls, essentially quadratic surface or one level higher. And if you really think about it, it's kind of a generalization of mesh. Mesh is kind of a union of, linear primitive, line, and polygon. So this one is a union, intersection, or difference of, higher cells, which may be ball, polyhedron, and such. So in this example, just take a cylinder and then use the new function or the new primitive, which represent a solid, a CGS object in this case. So I make the union of that cylinder and I rotate them. I rotate the cylinder, in this case, through a specific axis, and then I get the object here. So this is kind of a new representation, a new modeling scheme for geometry. And behind the scene, there is a lot of new shader, new rendering, and new computation scheme we put into place. I will give a talk tomorrow where I will explain more in details all the framework we have for constructive solid geometry. For the time being, I will just give you a brief overview of the set of features. As I say, for those constructive solid object, the base operation are intersection, union, and difference. So you can see it here where you can take essentially that, two cylinder and essentially do the intersection. Oops, let me resize this to be able to see that. There we go. So this is the intersection of the two cylinder. This is the difference, and this is the union. So those objects are fast to render and quite flexible to manipulate. And instead of basic primitive, I mean, usually constructive solid geometry is in 3D, but in our case, we always like to generalize from 1D to ND. So in terms of 2D, we can also do the same. So you can also represent solid object in 2D. And the basic set of primitive we have are this ellipsoid, parallelogram, rectangle, triangle, and regular polygon, and same places. Right. And as I said before, with same places, you pretty much represent all boundary mesh region also. So in this case, this CGS region actually will cover the mesh region, but it's a more flexible scheme for modeling than actually assembling, making just union of triangle of polygons. So in this case, you actually get this is an example of a disc and a triangle. You actually get the object there. And in dimension 3, this is the set of primitive you are supporting. And you can, if you might think about it, these are actually all the basic graphic or region primitive, which are mainly quadratic. So ball, disc, ball, capsule shape, cone, and such. But we also support, linear primitives, the trihedron and surplaces, right? As well as the new primitive, which is a torus there. Right? So you can take them and essentially use them to reconstruct, to model geometric solid object. So let's look at a concrete example. So this is a basic example. So this is coming from Alec, who just gave me a nice example there of a card object from a paper he randomly picked on the internet, and can we actually reconstruct it, right? So this is kind of the first initial step of a sample card modeling in the system. So essentially, you can first reconstruct, if you really think about it, you can reconstruct the base shape as a union of cylinders and cube. So you have the cylinder there, you have the cube, which is vertical, and you have the horizontal one. And the next thing you can do is essentially to construct essentially the object you will actually subtract or remove from the original set you have there. So here you probably will have to remove another set of cylinders. And if you make the difference of all of those, you get that object. So in a few lines, you can easily model object by just adding or subtracting other objects. So that's kind of the power of the constructive solid geometry, right? So that's kind of a more flexible scheme. And I'm sure you may ask, what's the difference with what we have already in terms of, for example, Boolean region, right, or region intersections, right? So this case is actually a subsystem we are building, which is essentially even closed in terms of Boolean operations. So it's kind of give a regularization. So if you make the difference of two solid region, you actually get a solid region or an empty set, pretty much. And it's closed under that, where for Boolean region, you actually don't get a closed set. And it's actually harder to model stuff with Boolean region because Boolean region is general. I mean, the first argument of Boolean region can take any arbitrary Boolean function, for example. And in this case, as you see the framework, you actually nest the expression progressively. And then at the end, you actually get a nice object in a few set of lines. Okay, so that was kind of a really brief overview of what we are introducing in this release. We continue to improve usability. Like every release, we'll do our best to improve usability so that the workflow is kind of fluid and everything just works. We'll continue to add more basic regions. Like in this case, we added torus and field torus. More analytic function for transformation. And our two main key features for this release, surface reconstruction and, our initial, set of functionality for constructive solid geometry. And I'm sure in the next coming release, we'll, extend more the usability, add more function for surface reconstructions. And, we also hope to actually jump to the next stage, which is, spline modeling, right? And get more close to CAD system and such representation. But also in a direction we are, you'll probably see us progressively add more integration with the Wolfram compiler, right? Like actually right now you have KD3 and, a set of, geometric search data structure already in the system. So we'll try to add more. For example, you have a CSG3 where you can actually manipulate your CSG region in the compiler and, just work on it. And you also kind of continue to, extend the connectivity, import and export, as well as direct connectivity to external system. So that's kind of, our future pipeline for the next release. So I hope that gives you a general view of what we are trying to do now in geometry and, try to kind of bring more, other geometric scheme and construction to the system. Before I close this talk, I would like to invite you to actually attend, different talk from the team, this computation team. So I like tomorrow we'll give a talk about the physical based rendering, material shading and other shading directive which have been introduced for 3D graphics. And J-Bomb will give a talk on the new feature in graph and networks. There's a lot of new feature, so stop by and we'll see that. And I will also give a talk on constructive geometry. So I will talk more in detail. So what's behind the scene and what's coming and all the nice set of features we plan for that. And also we'll have office hour for geometry and graph and network. So tomorrow from 11 to 2 p.m., we'll be giving, a set of talk and office hour. So feel free to stop by if you have questions and to look at the set of features we have. So thank you. And for the remaining minute we have, I will try to look at a couple of questions. So let's see. One first question is, does the cone object have a vertex with 2 cones? So our cone object essentially, well, if I open the documentation, our cone object essentially is, it have a base and a specified radius and then the vertex summit. So it's a predefined specific question for that. So there is a standard representation for that. So another question, can line and curve drawn on a sphere be projected onto a flat image using the GeoProjection feature in GeoGraphics? Well, I will leave that question, or give that question to Jose from GeoGraphic, but I believe there is a nice interplay between graphics and GeoGraphics, the same for geometry and graphics. So I'm guessing that should probably work. So let's see if there is another set of questions here on this chat. No. Okay, so that's pretty much a set of questions there. So if you have any more questions, feel free to stop to our office hour of geometry, which will be Friday at 1 p.m. Okay, thank you.